So similar to what we did with cylindrical systems, we can do very much the same kind of thing with spherical systems. And so this is conduction across spherical shells. So you might think about this, and this is, a thick-shelled, so you have a thick-shelled spherical container. So that's maybe one way to think about this. So for this thick-shelled spherical container, a lot of the same ideas hold. That is, that across any radial dimension in this shell, so whether we're at a radius of 1 meter or a radius of 1.5 meters into the system, if I have put in, for example, 100 watts into the system, then I'm going to get 100 watts out of the system at the other side of the shell. So if I've got this shell and 100 watts is being dissipated here, then 100 watts is going to come out of this shell at the largest radius of this system. Now, of course, the heat flux is going to decrease because the area has increased. So the heat flux decreases, but the total amount of heat transfer is the same. I think that's pretty clear. All right, so as before, we say that the heat transfer rate is dependent on the area and the heat flux. The area for a spherical element is just 4 pi r squared. And Fourier's law gives us what the heat flux is. By these statements that we've just made, we know that Q dot, the total heat transfer rate, is constant. So if we divide through by 4 pi k, we get that this Q dot over 4 pi k, which is equal to minus r squared dt dr, is in fact a constant. It's that same constant. It's the same kind of idea that we did before, where we're going to call this constant C1. I think then you know where we're going, because once we find out what C1 is, we're going to have a relationship between Q dot and delta T and over some radius. In fact, let's explicitly sort of go there. We want to find out what Q dot is in terms of delta T over R, resistance for a spherical system. And clearly, by knowing what C1 is, we're going to be able to get that. So in much the same way that we did it last time, we can divide C1 by R squared, and we recognize that we're going to be integrating this system. So what we're going to be doing is we're going to be integrating. We're going to have dt is equal to minus C1 over R squared dr. We're going to be integrating this, and in that integration, we're going to find out, so we're going to have two constants, C1 and C2, and we'll proceed as we did previously. All right, so as we said, this integration is going to result in C1 over R plus C2. So as you know, the integral of C1 over R squared dr is what we've looked at, and is going to be the C1 over R. And further, that using that and this constant of integration C2, that this is the result that we get. So this is a constant of integration and this is just that. So R minus 2 dr is just R minus 1. Okay, and so we have to apply boundary conditions much like what we did before. It's the same process that we did with the cylindrical system. and straightforward application of the boundary conditions, we can solve for C1. And so let's just fill in the gaps just a little bit here. So filling in the gaps is the fact that we have T1 is equal to C1 over R1 plus C2. T2 is equal to C1 over R2 plus C2. As we did before, we can subtract, and we say T1 minus T2 is equal to C1 1 over R1 minus 1 over R2. And clearly, the C2's cancel out, C2 minus C2. So that's 0. So we identify what C1 is as delta T over 1 over R1 minus 1 over R2. At this point, from the perspective of identifying what the resistance is, we're actually done. Because remember what we had before. We had that Q dot over 4 pi K is equal to C1. So that's the result that we had in our previous slide. And so understanding that C1 is just this T1 minus T2 over 1 over R1 minus 1 over R2, Q dot is 4 pi K T1 minus T2 over these 1 over the radius. Well, this, again, is equivalent to T1 minus T2 over 1 over R1 minus 1 over R2 over 4 pi K. So in some sense, from a resistance perspective, we're done. We know what the resistance is here. We know that the resistance for a spherical system is just 1 over R1 minus 1 over R2 over 4 pi K. So we'll show in the next couple of slides that this is the case. But if we wanted to get the temperature distribution, if we wanted to actually understand how T varied with R, then it's important for us to actually calculate what C2 is. So we can solve for C2 much in the same way that we did in the spherical case. So we understand that, remember, the way that we solve for C2 is we said that C2 is equal to this integration that we had here is equal to T minus C1 over R. So when we put particular values of T and R, so the pairs that we can put in, for example, T1, R1. That's the case that we're looking at here. So by putting that pair in, that there's a unique T1, R1, we are simply using the definition of C1 there, and the R1 multiplies, in the denominator multiplies the 1 over R1 to get this 1. The R1 multiplies 1 over R2 to get R1 over R2. And so we have a result for C2. So this actually result is that we know what the temperature distribution is. So this is a model or the prescription for what the temperature distribution is in a spherical shell. And that's a very powerful statement. It gives us all the information we need about how that varies. We see that it's a 1 over R dependence. We already gave or found this result because once we knew C1, we knew what the formulation was for the heat transfer rate. And as we identified before, we have a formulation for what the resistance is for these spherical systems.